Okay, one of the biggest strengths of our new quantum atom is that it's really reflective of what we observe in the periodic table. In this video, I think I've made mention of this in a couple other videos, but I just want to be really explicit about how our quantum atom is related to this periodic table. So what we can see then is we know that electrons should fill energy levels starting from the lowest energy going up to the highest energy level. So the first energy level, or the smallest, is the n equals 1, L equals 0 level, or the 1s2 level, that can hold a maximum of 2 electrons. And so when we're looking at our periodic table, we can see that in the first row we have two atoms, and that's associated with the 2 electrons that are available to fit into that shell. The next shell we would fill is the 2s shell, slightly bigger, still no rotation, so the lowest energy except for the first one. And what we can see here is we have lithium and beryllium filling those 2s shells. So here our periodic table is structured such that it's showing us the electrons filling in the right way. In our new atom, which tells us that we have 3 orientations for our p orbitals, means we should be able to fit 6 electrons into them at 2 each. And here we can see that's why we ended up with a block of 6 atoms at this location. The next shell to fill, slightly larger but no rotation, 3s2. And then we go to the 3p shell. Now, back when Mendeleev did this, he didn't know that this was the 3p shell. He just knew that these atoms were showing a similar chemical reactivity. But now we know the reason is because there are 6 atoms again that can take additional electrons before we run out of room and have to start that next shell. Again, we've talked about this trend a couple times now. The fact that energy doesn't go in the completely most obvious way due to the rotation of electron shells. So instead of filling the 3d shell next, we actually end up filling the 4s shell. We're here and we're going to the 4s shell next. And we have 2 atoms then that represent our alkaline earth alkali metals that are filling their 4s shell. And then we get 10 more electrons associated with the 10 atoms that could go into the 3d shell. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we can see then that the periodic table was really telling us about the different structure of subatomic orbitals that did exist and how many electrons can go in each cell by how many atoms were in each range. So the periods were telling us the atomic number, sort of, once we get to these tricky ones. They weren't quite right. And the columns were telling us the type of orbital. Now, what's interesting here is because of the order that we're filling in, these F don't even come in all the way down until these very bottom levels. And we can see, following our trend, 2, 6, 10, that these will be able to hold 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now on some periodic tables, they take one of these atoms and they put it in the top, or they take one of the atoms, or they take these 2 atoms and they sit them down here. So if you go and count this on your periodic table and you get 15, that's because they wanted to leave a space here to show where those atoms go. So they take 2 and they put them down. But it'll be 14 or 15, and the 14 are the F shells, and then if there is one, then the 15 is the first D shell. So that's how the structure of our periodic table and our quantum numbers agree with each other. And so this new atom came along, and probably the best piece of experimental evidence that showed that it was a reliable or a good model for the atom was the fact that for the first time we had a real clear explanation of why the periodic table was laid out the way that it was. It really was just a reflection of how many different electrons can fit into the different orbit levels.